and I'll also give some of the lectures. So the formal inauguration today is a holiday in Jamia. So the formal inauguration will happen tomorrow at 9:30. Okay. And there is a slight change in program. Actually, today the last lecture was supposed to be some computational package by Professor Refrizer, but he arrived late yesterday, very late night. So we thought that he just gives the lecture tomorrow. So there is a just interchange. The last lecture today, which was supposed to be the computational thing, that will happen the last lecture tomorrow. Okay, and today I will take that lecture. And tomorrow the first lecture will be the weak lensing one. Okay, the second lecture will be density perturbation, and the third lecture will be today's computational tools. And today the third lecture that I will continue. I will have one cosmology course lecture, so that I will continue to the third lecture. So that is a small change. So we have Professor Sanjay Jingan, our officiating director. So I asked him to say a few words, and then we can start.
Well, I informally welcome all of you here because tomorrow you'll be welcome formally. So, well, you're all very lucky because when you want to learn any art, I mean, it's very rare opinion that you learn from a master, and here you are the master himself. And weak lensing is based on one of the oldest tests of GR, the bending of light. And I'm sure in many of the cosmology lectures you have seen very beautiful arches, but they are strong lensing ones. I mean, weak lensing is really an art. And how it is done, how the game is played, I think you will learn through these lectures. So I welcome all of you here and welcome Professor Alexander to this series of lectures. Keep your mobiles off and try to focus. Thank you very much.
Okay.
Well, thank you, Anjan, for the introduction. And also thank you very much, Anjan, and the government of India for making this course possible. It's an honor for me to begin this course. I'm very happy to be back here to teach with Anjan this course. And also thank you for the Jamia Millia University to host this and also make this possible. So thank you very much. So as Anjan said, we'll be covering some part of cosmology and the way structures form, in particular the way we can learn cosmology from the formation of the large-scale structures of the universe. And in particular, we will learn how we can do this with this very special technique, which is called weak gravitational lensing. So we will start in a series of lectures. And today I will just start with the first lecture in cosmology, where I will give a very broad overview of cosmology, and in particular of the basic principles and also some of the observational tools, the principles of some of the observational tools we have available, and how does the weak gravitational lensing technique falls into this context. And then in the following lectures, we'll develop this in a lot more detail in a more theoretical and quantitative basis. So very broadly speaking, cosmology is the study of the universe as a whole. And it's a field that has seen very rapid progress in the last few decades. And it's now very impressive how cosmologists have now a quite precise picture of the history of the universe. So as you can see here, illustrated in this artist diagram, we basically, our cosmological model is based on the Big Bang paradigm, which is very simple. The idea is that at very early time, the universe was very hot and dense, and as the time evolved, the universe cooled down and expanded. And as a result of this cooling down and expansion, there was a number of phases or phase transitions that happened in the universe, leading to the universe that we know today, simply through this cooling down process and expansion process. There are many steps. Here I will simply talk about a few, and then of course we'll come back to some of the important ones later on. But following a very initial phase of very rapid expansion that we call inflation, then later on we entered what we called a particle physics era, where the universe was filled up with particles, and eventually the universe cooled down enough to form nuclei. And a little bit later, quite a bit later, the universe cooled down even further, and then nuclei and electrons could combine together and form atoms. And then later on, the universe cooled down even further. And then what happened is that the perturbations present in the early universe, so the small perturbations in the universe, could grow into the structures that we see today. And structures such as galaxies, clusters of galaxies, stars, and so on could start forming. And eventually, we come today, about 14 billion years later, and see and can observe this universe. Okay. Now, all of these stages are now quite well understood. And as I said, we'll come back through some of these important steps at different stages in the course. But before we do this, let's look at what the universe looks like today. So let's look at what the universe in particular is composed of. Well, first of all, of course, it's composed of what we call ordinary matter. In cosmology, we call this mostly baryons, which is kind of a misnomer, but that's what the terminology we use in cosmology. And the ordinary matter is basically, simply speaking, is the matter which is described by the standard model of particle physics, and it can be studied in the laboratory on Earth. It's also the matter, at least a fraction of this matter, is a matter that we see with our telescopes. So here is a picture called the Hubble Deep Field, which was at the time was still one of the deepest images done with the Hubble Space Telescope. And you see, just looking at a very small piece of the sky, a couple of arc minutes across, we see a very large number of galaxies, very, very distant galaxies of different colors and shapes. And the light that we see comes mainly from stars inside these galaxies. There are other processes like active galactic nuclei and others that produce the light. But basically, all of this, this image is made possible by photons emitted by ordinary matter and traveling all the way to us. So this is the matter that we understand, that we used to, that we can study on Earth. Now, the problem is that when we look at the fraction of the energy density in the universe composed of this ordinary matter, so if you take the full energy density of the universe today, and say this is 100%, will be all the way up here, the amount of ordinary matter, the fraction of this total energy density composed of ordinary matter is very small. It's typically of order 5% or so. So while in physics we've been mostly focusing on this kind of matter, actually it represents only a small fraction of the total energy density of the universe. So then the question is, what is the rest of the universe made up of? Well, there are different components. And the first one is dark matter, which is a form of matter which by construction is dark, so we cannot see it directly. It was, in fact, there's quite a long history of dark matter. It was initially postulated by Zwicky in the 30s. He didn't call it dark matter, he called it missing mass or other terms. But basically, Zwicky noticed that in order to, he was looking at structures like clusters of galaxies, which you saw here. We'll come back to it later. These are the largest bound structures in the universe. These are large structures made up of, composed of galaxies, typically 1,000 galaxies or so. And if he studied the dynamics of these galaxies, how these galaxies move inside the cluster, and looking at the random motions, he could infer the gravitational potential in which these galaxies had to sit in order to have these kind of dynamics, this kind of velocities. And he noticed that there's a need for a large amount of mass, which is unseen, in order to explain the dynamics of these galaxies. So he had to say there is much more mass than we can account for by looking only at the visible matter emitted by the galaxies. All right. Then there's a long history, and there's now a large amount of evidence in astrophysics, astrophysical evidence for the presence of dark matter. We basically need to invoke this additional matter, this unseen matter, on basically all cosmological scales, going from galaxies to clusters of galaxies, and even at the largest cosmological scale. By construction, the dark matter does not emit light, because otherwise we would see it. And the only evidence we have about dark matter is through its gravitational effect. So we see it through gravity. The source of gravity is any form of energy or mass in this case, and therefore it affects the trajectories of objects orbiting in its vicinity. And as we'll see later, it also affects the trajectory of photons. And this is the basis of the gravitational lensing effect that we'll be focusing on later on. We know some of its properties from cosmological observations. We know that it has to be very weakly interacting, either with ordinary matter or with itself. Otherwise, if it interacted more strongly with ordinary matter, we would see it eventually. We will see eventually a decay into photons and we know that we have upper limits about this. We also know that it cannot interact very strongly with itself. Otherwise, it will change the properties of the distribution of the dark matter that we can observe through gravitational lensing effect or other effects as well. We know that it has to be cold, or another way to say this has to be non-relativistic. Again, if that were not the case, it would change the kind of structure that we observe today, and we know that the structures that we see are compatible with these non-relativistic or so-called cold dark matter. We also know that it cannot be made of ordinary matter. You could say maybe part of the ordinary matter is dark and we cannot see it, and indeed that's true. We can only observe directly with our telescopes a fraction of the ordinary matter. But the fraction that we don't observe falls short from explaining the entire mass density we need in dark matter. So it's so-called non-baryonic, so it's not made up of ordinary matter. We also know that this distribution is relatively smooth, and there are very strong constraints on the granularity of the dark matter. So we know the dark matter is not made up of macroscopic objects of the size of stars or planets or so on. So it's very likely to be a very smooth, most probably a microscopic component. And therefore, there's a number of candidates for the nature of dark matter. And the favorite candidate is basically to think of dark matter as an unknown particle, which is not part of the standard model of particle physics, so it's not part of ordinary matter. And therefore, there are searches for these unknown particles beyond the standard model of particle physics. And there's a very large amount of work now being done into trying to detect or produce particles that basically form the dark matter. Now, if we look at the amount of dark matter in the universe, and again, throughout the course, we'll show you how we can determine this fraction, then we see that indeed the amount of dark matter is much higher than the amount of ordinary matter. It's about 27% of the current energy density of the universe. However, it still falls short from explaining the entire energy density of the universe. By the way, I think we're keeping this interactive, so if you have any questions, please don't hesitate to interrupt me and ask.
You mentioned about the dark matter particles.
Mm-hmm.
They must decay into standard model particles to be able to detect.
Yes. Well, they must. It's very likely to be the case. Yes. So there are searches for what we call indirect searches for dark matter, which are basically search. Eventually, it probably will turn into photons, most likely high-energy photons. So there are searches for photons arising from annihilation of dark matter with itself or with ordinary matter. And for the moment, there's some very interesting improvements in these limits. For the moment, there's no clear evidence for having found this decay, but the searches are ongoing, especially with gamma ray telescopes, and there's even a new experiment are being designed in order to do this. Yeah. So there are basically several ways of looking for this dark matter. Either we can look at it from astrophysical observations through its gravitational interaction, which is what we'll be talking about here. You can also look for them through indirect detection by looking at decays of dark matter or interaction of dark matter with ordinary matter. It's known to be very weak, but it may not be completely, it may not vanish completely, and then we would see this indirect, photons coming from this interaction. That's called indirect dark matter search. There's also direct detection, so people try to detect interaction of dark matter with ordinary matter by putting very large amounts of material and wait for a dark matter particle to interact with a nucleus in particular. And there's also accelerator-based searches where particle physicists try to produce by going to very high energies to produce dark matter particles which eventually decay into something that we can see. So there's these four methods for studying and detecting dark matter, and each of them are a very, very active field of research. So that's a good question. Yeah.
Regarding the granular size of dark matter, there was a very recent paper which said that primordial black holes,
yes.
Considering primordial black holes to be constituted of dark matter itself.
That's right. So there's still a very narrow parameter space of macroscopic objects that could make up dark matter, especially on the high end. And following the detection of gravitational waves, the report of detection of gravitational waves by LIGO, there was a report saying that perhaps what they've seen is dark matter in the form of black holes of about 100 solar masses or so. So we'll talk a little bit later. So most of these limits on granularity, or what I call granularity, come from this microlensing technique, which try to detect gravitational lensing effect, gravitational effects coming from macroscopic objects in our galaxy. And indeed, it rules out some masses of a possible macroscopic object that could make up dark matter, but not all of them completely. Okay? But it's relatively narrow, so it's an interesting paper, certainly worth looking at, especially the LIGO results are particularly interesting, and the mass of these black holes are sort of puzzling. But the parameter space is quite small. So people have been focusing until recently on microscopic on microscopic models, or models where the dark matter is microscopic in the form of particles. But that's true. That's right. I was a little bit careful when I stated this statement. But that's at least our standard model currently is through through particle explanations for dark matter with weakly interacting particles. Any other question? No? So that's dark matter. Okay, so climbing up, we're getting there. We now have about 30% of the energy density of the universe today that well, I wouldn't say that we understand, but at least of which we know the different ingredients. And then what is the rest of the energy density made up of? Well, this is something even more mysterious called dark energy. Okay, so what is this dark energy? And Anjan works a lot on dark energy. You can ask him even more details about this from a theoretical point of view. So dark energy is something we don't understand at all, but it's a term or a word we give to a phenomenon that we see in the observations and that we don't understand, and for which we have a number of possible explanations, but it's very puzzling. So basically what we see through the observation, and I'll come to the observations in a minute, how we know all of this. What we see, one of the things we see in the observations is that if we look at the expansion of the universe as a function of time, so this is a simple diagram that shows time on the x-axis and sort of the relative size of the universe, so basically the expansion history of the universe. What we see is that the universe has recently starting to accelerate. The expansion of the universe has recently started to accelerate. Okay, and that cannot be explained if we fill the universe with matter or even dark matter, so any kind of form of matter or even radiation, even relativistic particles. If we fill the universe with any of these kind of matter, ordinary matter, or nothing exotic, then the universe would, depending on the amount of matter, would expand and slow down, would expand, could even recollapse, but would not be accelerating like this. So there's something else in the universe which produces an acceleration of the expansion, which is sort of started at our cosmological epoch. Okay, so it's very puzzling. Now, what can it be? Well, there are many possibilities, but one way to think about it is to think of it as an effective fluid that we add into the universe. Okay, it's kind of a phenomenological description of this dark energy, and this fluid can be given basically an equation of state, and we can parameterize phenomenologically this equation of state with a parameter that we call W, which is called the equation of state parameter, which is the ratio of the pressure to the density of dark energy. And it turns out that to produce this acceleration, we need this ratio to be negative. There are other conditions as well. So it means, another way to say this is that we basically need a negative, sort of an effective fluid something that behaves like an effective fluid with negative pressure, which is really quite a strange kind of fluid indeed. Another way to say this is we need basically some kind of repulsive gravitational effect, which is very puzzling also because we know that at least in our standard view of gravity, gravity is only attractive. But here we need some kind of repulsive gravitational effect to produce this acceleration. Now, there are many models for explaining dark energy. Again, Anjan can tell you a lot of them. He's worked on many of them, and other people here. But one of the sort of the standard one that we invoke, at least for our standard model of cosmology, is the cosmological constant that we for which the symbol is capital lambda here, which would correspond to W, this equation of state parameter, equal to -1 at all times. So in units of C equals to 1, the pressure and the density, ratio of pressure density of this effective fluid, at least phenomenologically, will be constant and equal to -1. Now, the history of the cosmological constant is quite interesting because it was initially introduced by Einstein for sort of the opposite reason. So in the early development of general relativity, soon after Einstein wrote down the equation of general relativity, he and others solved for a solution for the whole universe. And what they found is they found solution for where the universe was expanding. Now, of course, we now know the universe is expanding. By the time they didn't know this. And in fact, there was a theoretical, perhaps even philosophical prejudice that the universe had to be static. And they found an expanding universe a way too exotic possibility for the universe. So Einstein added this cosmological constant in his equations of general relativity to make the universe static. And later on, when the expansion of the universe was discovered observationally by Hubble, Lemaitre, and others, then it was established that the universe was indeed expanding. And at least the story says that Einstein realized it was his biggest mistake or biggest blunder. It's not clear actually if he actually said it, but it's at least what the story we tell. Now, paradoxically, actually, perhaps what he called his biggest blunder happens to be correct. And indeed, we indeed need a cosmological constant-like term in the equation, or something that behaves like it or closely like it, with an opposite sign here, because we're not trying to make the universe static, or the other way, we try to make it expand, to accelerate the expansion. But nevertheless, one explanation for dark energy would be an Einstein cosmological constant with an opposite sign that Einstein invoked. And this would, as I said, correspond to this equation of state parameter equal -1. There are many other models based on dynamic scalar fields and others which are also being explored. And these would have, more generally, an equation of state parameter, an effective equation of state parameter that would not be equal to -1 or not exactly equal to -1, and would generically at least vary as a function of time, of cosmological time. So one of the searches right now is to try to determine this, to measure this parameter W as a function of time, to check that indeed dark energy behaves exactly like a cosmological constant, or whether it behaves like the prediction from some of these other models. Now, the problem with dark energy is that it's very difficult to reconcile with the understanding of the vacuum, in particular with the quantum mechanics of the vacuum. We know that the vacuum, if we look at the quantum mechanics, the physics, the quantum mechanics of the vacuum, we know that basically there's an energy density coming from quantum fluctuations that indeed gives it a non-negative density. However, the scale of this energy, of the energy density of this known quantum vacuum is at least 30 orders of magnitude larger than what we observe today. So it's off by at least 30 orders of magnitude. And that's why physicists think that there's a mechanism to suppress this vacuum energy density, or this vacuum energy, to zero. And it's very difficult to understand how this very large energy could be suppressed, but not to zero, but to a value 30 orders of magnitude below. which is very close to the scale of the dark energy density that we see today, and which also the same order of magnitude as the energy density of dark matter, which has nothing to do, as far as we think, with the quantum mechanics of the vacuum. So while dark matter is a phenomenon that we don't understand, but for which we have many possible explanations from extensions of the standard model of particle physics, here, dark energy is very puzzling because it's very hard to reconcile with some of the fundamental pillars of microscopic physics. So dark energy is indeed a very great puzzle. Now, underlying to all this is the nature of gravity. So one of the fundamental ingredients in cosmology, in the physics of the universe, is gravity, which is a driving force, the main interaction for the universe. And in fact, when we look at gravity, our theory of gravity is called general relativity. And one of the possibilities is that some of these phenomena, either dark energy or dark matter, are related to the fact that we need to modify Einstein's theory of general relativity, at least on cosmological scales. And there's also a large amount of work being done on the theoretical side to see whether we could modify Einstein's theory of general relativity to explain one or two or several of these dark ingredients that we need to invoke in order to explain the observations. So possibly it's our fundamental understanding of gravity that needs to be revised. Another very interesting aspect of the model that is also being explored is the problem of the initial conditions. What is the physics that set up the initial conditions in the universe, and in particular, what is the origin of the perturbations that grew to form the structures that we see today? And in our standard model, the paradigm is called inflation, and that also has a number of open questions that is still being worked on. So together, you see that if we look at this more globally, we see that we've come up with a very precise picture of the universe, but we had to add a number of ingredients in our model to explain the observations, and that leaves open a number of very pressing and fundamental questions in physics to explain these phenomena, such as dark matter, dark energy, possible modifications of gravity on very large scales, and also the theory of inflation for initial conditions. Any questions about this? Again, we'll come back to these more quantitatively later on in the course. Now, how do we know all this? Okay, so I give you the sort of the bottom line of what the universe is made up and the main ingredients in our current cosmological model. But how do we know all of this? Well, there's basically two handles that we have, two physical handle that we have to study the universe and to constrain our cosmological model. And one of them is what we call geometrical handles, and another one is those based on the growth of structure. So let's talk about each of them, at least qualitatively. So first thing we can do is we can try to probe the geometry of the universe, or more another way to say it, we can probe the global expansion history of the universe by looking at what we call geometrical probes. So an example of this is to consider an observer here, and let's consider the observer looks at a standard stick, which is some distance away, cosmological distance away from the observer. Now the universe is expanding, so the stick, let's suppose the stick has a fixed size in physical coordinates, so it has a fixed physical size, and let's suppose that it expands with the universe. Now as the universe expands, the stick will become larger and larger, so as we observe the stick, if we could observe the stick at different distances, which in cosmology correspond to different times, because light takes time to travel from us to the source, then the stick would grow. And then what we could do, in simple terms, we could say, let's suppose we can measure the apparent angular size of this object. All right, so let's say it's here. It has this physical size, it would subtend this angle here. And as it becomes closer and closer, so the universe, as a result, we're seeing it at later times, so the stick has expanded. With the expansion of the universe, then it would subtend a different angle. All right. Then what we could do is we could measure the relationship between the apparent size of the object and its distance, and that would give us a measure of the expansion of the universe. Okay. And that is called a standard ruler. Okay. So if we could find a standard ruler which we know has a fixed size and expands with the universe, then we could measure the apparent size of this standard ruler as a function of its distance, and we can probe the expansion history of the universe. We can also do it not with a standard ruler, but we'll see later we can do it with a standard, so-called standard candle, which is a source of a known luminosity. And as a function of distance, it would have a different apparent flux, which would again depend on the distance, which would allow us to probe the expansion of the universe. All right, so these way of measuring are purely probing the global geometry of the universe and the global expansion. Another handle that we have is based on the growth of structures. Okay, so this probes the way density perturbations grow as a function of time. And as a result, it probes the formation of the structure that we see today. Now, it turns out that the growth of structure is a competition between two effects. So if you think about two blobs here, denoted by these blue spheres, then basically we have two effects. On the one hand, gravity tries to pull these two blobs together. So it tries to, it attracts the two blobs, so it tries to make structures grow. On the other hand, the expansion of the universe tries to pull them apart. So the way the growth of structures in the universe is basically a competition between gravity and the expansion of the universe. And therefore, by studying the way the structures grow as a function of time, we can again probe, and we assume we know gravity, so we assume we know gravity the physics of gravity is given by general relativity. Then once again, we can probe the expansion of the universe. So this is another way of studying these dark ingredients, or cosmological model, by studying not only the global expansion, but also the way perturbations grow in the universe. And again, we'll be coming back to that later on in the course. Now, more precisely, how can we make these measurements? Well, to do this, we rely on what we call cosmological probes. So there are different ways where we can measure these. There are different ways where we can measure both the geometry, the growth of structure, or a combination of these two effects. And what we do is we measure this in different ways through different probes, and then we combine these probes together to constrain our model. And the reason we do this is for various reasons. First of all, it helps to get better constraints on our model because we can combine different measurements. Okay, and also it also helps to overcome a difficulty in cosmology, which is the fact that cosmology is an observational science as opposed to an experimental science. By this I mean that in cosmology we rely on observations, but we cannot go and modify the system to simplify it and to isolate a phenomenon. We can only rely on observation, which means that the phenomena are complex and need to be disentangled. It's not like a physics experiment where we can design the experiment to isolate a certain phenomena that we want to measure. Here we have to deal with all the phenomena together and find windows where we can make precise inference on the system. But there's always a complicated effects and astrophysical effect that we need to disentangle. So by combining these different cosmological probes, the advantage is that we have different what we call systematic effects, or different astrophysical phenomena that we need to disentangle, and by combining them we can get around that and get a more certain measurement of the underlying physics in our model. So basically there are different classes of cosmological probes, and I'll be talking about each of them one by one very briefly now. And of course, one of the main focus of the course is this gravitational lensing probe, which is which has a special place in cosmology, as I'll soon explain. At a very important phase transition in the universe, which is when the first atoms formed, so when nuclei and electrons combine to forming atoms. And this has a very important consequence for the universe, is that the universe suddenly became neutral, and as a result, photons suddenly could travel freely into the universe. Another way to say this is that the universe suddenly, very soon, became transparent to photons. So suddenly the universe became transparent. And this happened at energy scales or temperatures about corresponding to 1 electron volt or so. And the idea is that before this, the electrons and photons, or the baryons and photons were tightly coupled due to very strong interactions between the ionized plasma and the photons. And as the atoms formed, then photons suddenly had a very small interaction, cross-section with the baryons, and the photons could travel freely. So it means that we can see photons up to this last interaction that they had with the baryons, and that is called the last scattering surface. And we can now measure this very precisely. So this is a picture of the cosmic microwave background, or a measurement of the cosmic microwave background done by the Planck collaboration. The Planck is a satellite that was recently launched, and for which very high precision measurements were made. And what you see is a picture of this last scattering surface. What is plotted here is a temperature of the cosmic microwave background. The mean temperature is around 3 Kelvin, but there are very small fluctuations that you see here, which corresponds to fluctuation of temperature in about 1 part in 10 to the 4 also. Yep. Sure.
Question. So there is a statistical effect.
Mm-hmm.
You just take a patch of space,
Yes.
see number of photons, and measure the temperature.
Yes.
How do you achieve this accuracy?
Well, that's very difficult. Very difficult, with great difficulty, that's the answer. But basically what they have to do is, that's why they go to space. They also have measurements from the ground, but basically you have to cool down your apparatus to very low temperatures, and there are different technologies to measure. So this is done in the microwave, all right? And what they do is they have detectors with different technologies. With Planck, it's basically bolometer technologies that allows them to measure the flux, basically, of the photons, from which they can infer the temperature. Okay? So what they do is they measure the flux of the photons in different patches of the sky by scanning the sky. They do it in different frequencies, which allows them to get a temperature measurement, because the cosmic microwave background follows very closely a Planck blackbody spectrum. In fact, it's remarkably close to a blackbody spectrum. They use also the multi-frequencies to disentangle other astrophysical effects. There's quite a lot of work in particular, removing the foregrounds from our own galaxy, which also emit in the microwave region. And then from that, they can get a map like this of the temperature. Okay? But it's a very, very high-tech, low-temperature bolometer technologies, basically.
So you're reaching 4th decimal place.
Yes. Yeah, microkelvin kind of. Yes, that's right. That's right. It's extremely impressive measurements from the experimental point of view. There's also a big effort to do it from the ground, and there's an ongoing measurements now, especially in the South Pole and also in Chile, for measuring this, and more advanced statistics I'll talk about in a minute. And that's an ongoing research frontier right now.
So my question was that, like in gravitational wave detectors, we recycle the photons and all that stuff to increase sensitivity.
Right.
I never understood how they use that.
Yeah. Well, it's I mean, it's it's very impressive. And one thing that helps us also, what we need to do is differential measurements from one place to the other, right? We measure the absolute temperature in different ways as well. Okay, so we get a map like this of the temperature fluctuations. And then, of course, so this basically gives us a picture of the universe at early times. Basically, the state, at least the state of the structures in the universe at early times. It shows that the universe was very much homogeneous, but there were very small perturbations of the order of 10 to minus 4 at that time that are now mapped by these measurements. Now, what we can do with this is take this map and then measure the statistical properties of these perturbations. And that's extremely rich in information. So we can, what is done is we can take a Fourier transform. So this is on a sphere, so we can take a spherical Fourier transform of this map and measure what is called the spherical harmonic power spectrum of these fluctuations. And what is shown here is one of the latest measurements by the Planck surveyor team. And what is shown here is the so-called multiple moments, so it's kind of the Fourier mode. On the x-axis and the y-axis is the amplitude of the perturbation on these scales. So this corresponds to inverse angular scales, so this corresponds to large scales on the sky, this corresponds to small scales. And here it shows the amount of fluctuations or deviations from constant temperature as a function of this scale. Okay, so this corresponds to large-scale fluctuation, this corresponds to small-scale fluctuation. Scale in a convenient way. And you see now the quality of the measurements. So you see the blue points with error bars. Forget the red line for a second. You notice that they're extremely good measurement now. You can barely see the error bars on this plot. Extremely impressive. We also see that there's a number of features which are extremely well measured and resolved by these measurements. And you see that there's quite a wide range of scales and with these so-called oscillations or wiggles that we see in the power spectrum. You also see that on large scales here, the errors are larger. And that's coming from a phenomenon called cosmic variance, which is the fact that since we only have one sky, we only have a few large-scale modes, Fourier modes, or spherical harmonic modes that we can measure. So the errors increase on large scales due to the fact we only have one sky. And if you plotted this to a smaller scale, you will see also the error bars increase. You can sort of see it in the residual here. On small scales, that's because on small scales we can start seeing the effect of the finite sensitivity and resolution of the experiment. Eventually, the errors increase because of this. Okay. And these wiggles are very important. They basically arise from plasma physics, basically. So they come from acoustic oscillations, sound waves, in the photon baryon fluid at the time of last scattering. And they provide a lot of cosmological information that depend on the amount of dark matter. They depend on the total density of the universe. They depend on the amount of baryons, ordinary matter, and so on and so on. And what you see here in this red line is a fit to this data point with our standard cosmological model that we call lambda CDM. I'll come back to that a bit later, with 6 parameters. And you see the excellent fit between the data and the model. And that's the residual in the fit. And that's where we get a lot of our cosmological information, as I said. Now, in the cosmic microwave background, one can measure more than the temperature. That's even more difficult. And in fact, it's still sort of the very, very large effort is being done here. We can measure not only the temperature fluctuations, but we can also measure the polarization of the photons. So it turns out that the microwave background is also polarized, and that's symbolized by these lines here that describe sort of the polarization direction of the photons. And there are patterns in this polarization, just like there are patterns in the temperature fluctuations. Okay? And very interestingly, one can decompose these polarization patterns into different so-called modes, which are shown here. They're called E modes and B modes, following an analogy with electricity and magnetism. So basically, you can take any polarization field like this, which you think is basically arrowless vector at every point on a sphere here, or you can do it on the plane as well. So this corresponds to a special spin 2 field, which basically so it's like a vector but doesn't have an arrow, so it goes back to itself if you rotate by 180 degrees. And you can show that any such field can be decomposed into two components. One is the electric-like modes, and one is the magnetic-like modes. So the electric modes have no handedness, so they're the same if you look at them in a mirror, while the B modes have a handedness, so the patterns flip if you look at them in a mirror. And you can, in a unique way, at least in the absence of noise and finite resolution and so on, you can uniquely decompose these patterns into E and B modes and measure, therefore, not one power spectrum, but several power spectra. And that's what this is the measurement from the Planck team. You see the measurement of the E modes here, and some of the cross correlation. So this is the E mode power spectrum. This is the cross power spectrum between the temperature and the E modes. And you see again now very clear measurements of these polarization power spectra and cross power spectra, again with small error bars and very good fit to our cosmological model. And together, these can be combined to give us a very tight constraint on our cosmological model. And if you look at the Planck papers, you get tables like this. So the point is not to read all these numbers. That's obviously too small. You probably can't even see them. But the idea is just to show the sort of size of the precision of the measurement. So these are the 6 parameters of this standard model of cosmology, which we call lambda CDM, which is basically general relativity plus cold dark matter plus ordinary matter described by the standard model of particle physics, plus a cosmological constant, and plus an inflationary phase to provide the initial conditions. And these are the constraints that the team gets on the 6 parameter of this model. The different columns correspond to the amount of information they use, with increasing amount of information being used here, especially adding polarization or adding some of the other cosmological probes that I'll be describing next. And if you just look at the size of these errors, so you see that we get % or sub% precision on these parameters. Extremely impressive measurements. Now, if we expand the model and start looking at the precision one gets on the dark energy parameters, so here this is assuming that the dark energy is made up of consists of the cosmological constant, which, remember, correspond to an equation of state for the dark energy effective fluid equals to -1 at all times. Well, you can start making a Taylor expansion of this equation of state parameter, W, and think that you can look at its value today and its derivative as a function of time. So you can characterize the evolution, the value of the equation of state parameter for dark energy and its equation and its evolution with 2 parameters and start constraining this parameter. So this is basically an expansion of the standard model, this lambda CDM model, in which the dark energy is no longer a cosmological constant, but something more complicated with an evolving equation of state. And you can start constraining it. And basically, what we see, so this is W, and this is the derivative of W. So if it's a cosmological constant, W should be equal to -1 at all times. So it should be here. That's -1 for W, and all time means the derivative is 0. So that corresponds to the intersection of these 2 lines, so you correspond to this point. And if you combine various cosmological probes with the CMB, you get typically constrained like this. It depends exactly what you combine with what, but sort of the typical current constraints correspond to these contours, where you see that the contours so this corresponds to different confidence levels, and these contours are consistent with the cosmological constant, but still with the relatively large error bars as to its value, typically 5 to 10%, and with typically 10 to 20% error on the equation of state parameter here. So it's consistent with the cosmological constant, but there's still room for the possibility that other models of dark energy is valid.
You mentioned
yeah.
the assumption of inflationary area also goes into this.
Yes.
So how sensitive are these numbers to what, and what you choose specifically?
Yeah, so what you assume really is that you have to assume that, what you really assume is that you have you know the properties of the fluctuations before the surface of last scattering. So in other words, you say that you know the property of the fluctuations at early times. And here it is assumed that you think that the perturbations have a power spectrum which is a simple power law with an unknown amplitude and a slope. And for instance, two of these parameters characterize this amplitude and this slope. So this is the amplitude of the power spectrum, and this is the slope. All right? And inflation generically, standard implementation of inflation generically predict to a good approximation a power law with a slope close to 1 with a small deviation. And that's indeed what we see. Basically, the slope here is very close to 1, and the amplitude is given by this. So strictly speaking, what you need is, purely for the CMB, all you need is to have a special kind of fluctuation called adiabatic fluctuations in this model. So special kind of ratio between the fluctuation different components with this power law regime, and then you can constrain the power law. And these come out naturally from the inflation models. Now, the inflation models also predict relation between these fluctuations and the polarization fluctuation, which arise from actually gravitational waves in the early universe. And so by looking for these polarization modes, you can also constrain inflation even further.
Do strong gravitational events have an effect on CMB, isotropy of CMB?
What do you mean by strong gravitational events?
One that is producing highly intense gravitational waves, like collapsing black holes.
Collapsing black holes, it depends. Well, it depends on the kind of models that you consider, but and it depends how many you have. But the ones that can be observed with gravitational wave detectors would have a relatively small effect here. What is there is that also gravitational waves produced in the very early universe, which produce a gravitational wave background, and that has an effect. And in fact, it's one of the things that are being searched for through the polarization measurements. They're basically, we're looking at different frequency modes that are relevant for this. Okay. So that's the cosmic microwave background, which, as I said, is sort of the driver right now for cosmological information. But in order to learn more about the universe, and in particular in order to constrain dark energy better, one needs to probe the universe at late time, so close to a cosmological epoch, which is when dark energy is important. As I told you, dark energy is a word for the accelerated expansions at late times, at our epoch, while the cosmic microwave background, for the most part, probes stages of the universe which are earlier than this. It's also sensitive in other ways, but the primary informations come from early times. So what we need is to have more information at late times or in a more local universe. And this is done by studying a large-scale structure in the more local universe. And one of the ways of doing it is through galaxy surveys. So how much time do you have? No, 10 minutes or so?
We have another 20 minutes.
20 minutes, good, very good. So the way to do this is look at galaxy surveys, which probe the more local universe. And this is a picture of one of the surveys. There are now there has been two main surveys that have given us a very accurate map. One is called the SDSS, Sloan Digital Sky Survey, and the 2DF surveys. And what you get is typically pictures like this. So what is shown here in the different color scale is the density of galaxies as a function of position. So the red regions correspond to places where there's very large density of galaxies, and the blue ones correspond to places where there's very low density of galaxies. And this is mapped in three-dimensional and spherical geometry, because these galaxy surveys can give us three-dimensional information about the position of galaxies by the measurement of not only the position of the galaxies in the sky, but also a measure of its radial distance using the redshift of the galaxies. Okay. So we get a distribution like this. So you see that the distribution of galaxies is not homogeneous. I mean, it's homogeneous when you smooth it on sufficiently large scales, like 100 megaparsec or so. But when you look at smaller scales, there's a lot of inhomogeneities. You see there are denser regions, there are different bubbles, there's all sorts of filaments, also complicated distribution. And what one can do is we can do an analysis similar to what was done with the cosmic microwave background. One can look at the statistical properties of the distribution of these galaxies, except this time it's in 3 dimensions, right? With the cosmic microwave background, it was a 2-dimensional spherical map. Here it's a 3-dimensional distribution, but we can do an analysis which is sort of similar, and we can look at what we call the galaxy power spectrum. So this is a power spectrum of the density of galaxies in the universe. And this is a typical measurement. This is done with by the Sloan Digital Sky Survey, survey called BOSS. And what you get is measurement like this. So again, this is the inverse scale here, except now it's no longer angular scale, it's physical scale. So this is basically the Fourier mode. You do a Fourier analysis and you look at the Fourier modes. So this corresponds to large scale, this corresponds to small scales. And here again is the amplitude of the fluctuations of the number of galaxies as a function of scale, all right? Scale in a convenient way. And one gets now this very good measurement for the power spectrum of galaxies. You see a smooth oops, what have I done here? You get a smooth behavior here, but you also get these wiggles here in the power spectrum. And if you remove the smooth part from the, subtract the smooth part and you look at the residual, you get these clear oscillations as well. Okay. Now, for the galaxy power spectrum, there's a lot of information actually in the power spectrum, and different information one can extract. One thing one can do is look at the full shape of the power spectrum, okay, and compare to a model for structure formation, just like we compared the CMB power spectrum with the prediction for our cosmological model, and infer cosmology from it. Now, the difficulty with galaxies is that what we observe is not the density perturbations directly, which is what the model predicts. So the model will predict the fluctuation of mass, basically, or density fluctuations. But what we observe instead is the distribution of galaxies, which is not quite the same as the distribution of mass. We think galaxies trace the mass, but not exactly, and in a slightly complicated way. And the way to characterize or quantify the relationship between the mass and the density perturbations and the galaxies, or another way to quantify the relationship between mass and the visible matter that we observe through the galaxies, we introduced the notion of galaxy bias, which was introduced by Nick Kaiser, and now has a lot of work being done on it. So the idea, at least in simple terms, is that you can relate the power spectrum of galaxies, which depends on scale or Fourier mode, and redshift, because it evolves as a function of redshift, or it evolves as a function of time. And you can relate it to the power spectrum of the density perturbations, which is what we can predict from theory, and Anjan will describe some of the physics of that. So you take the galaxy power spectrum is equal to the density power spectrum, or we call it the matter power spectrum, times a quantity here which we call the bias, which can evolve with redshift, and could, at least on some scale, also depend on scale. Now, if we go to sufficiently large scales, we have good theoretical reasons to believe that the bias only depends on redshift and not on scale, because we think that these scales are still in a linear regime, and therefore it's a good approximation to think of this bias as a function of redshift, but not of k. Okay, so another way to say this, if we measure the galaxy power spectrum at a given redshift on these large scales, then we can get a measure of the density power spectrum or the matter power spectrum up to a constant that we don't know. So we can't really use the amplitude, but we can use the shape of the power spectrum, at least on large scales. The amplitude, of course, gives us something interesting. It gives us something about information about the physics of the formation of galaxies. So astrophysically, it's very interesting, but for cosmology, we cannot use it directly. But nevertheless, if we make these assumptions, or if we model the bias carefully and so on, one can try and use the entire shape of the galaxy power spectrum. Now, that's one thing we can do, and that's where you would get the most amount of information. But one can try to be more conservative and use only some features of the galaxy power spectrum which are less sensitive or barely not sensitive to this assumption about bias. And one of the very powerful way of doing this is by studying what is called these baryon acoustic oscillations, which are basically these wiggles, right? So it turns out that, and that's quite remarkable, that these wiggles that you see here are basically the same physics as the wiggles you saw in the cosmic microwave background fluctuations. And they're basically coming from the same acoustic oscillation, the same sound waves at the surface of last scattering. And now they're not imprinted, well, we don't see it through the imprint on the fluctuations in the cosmic microwave background radiation. We observe it through the imprint of these acoustic waves on the galaxy power spectrum. And they've now, as I said, been measured quite well. And we can do a lot of things with it, but the simplest thing one can do is we can just measure the position of the first peak or one of the troughs of these wiggles. And we can relate it to the physics of these acoustic oscillations. It turns out that's relatively well-known physics, basically plasma physics. It's related to the sound wave of these acoustic oscillations at the surface of last scattering. And we have good reasons to believe that, at least given the information the cosmic microwave background is giving us, that the scale of these first acoustic peaks is around 100 megaparsec or so. All right? And so that gives us basically a standard stick. So this, at least if we're in a linear regime, we have a scale for these oscillations that is fixed in co-moving coordinates, and then we can measure that at different redshift and get a measurement of the geometry. And what is interesting is that we can do it both in the transverse. So if we look at the line of sight, we can measure this both in the transverse direction, so in the direction of the plane of the surface of the sky. We can measure it basically in angular. We can measure the baryon acoustic oscillation peaks in the angular direction. We can also measure it in the radial direction. That gives us additional information and the complementary information. And from this, we can get a pure geometrical measure through this measurement of the power spectrum wiggles like this. So even though we're using the density perturbation and the growth of structure here, we've isolated a feature in it that gives us a pure geometrical measure, which is very powerful and much less sensitive on the bias. Another very interesting piece of information is called redshift space distortions. And this comes from the fact that when we look at the position of galaxies, the radial direction is very special compared to the transverse direction. So the transverse direction, we can directly measure to measure the transverse position of galaxies, we can just measure the position of galaxies on the sky. So that's relatively easy. But to measure the radial direction, we don't have a measure of distance directly. What we can measure is the redshift of the galaxies, which is the redshifting effect coming from the expansion, and which is larger and larger as the galaxies are further and further away. So that gives us a proxy of the distance, of the radial distance of the galaxy, but it's not exactly the radial distance of the galaxy. In particular, if the galaxies are also moving with respect to the Hubble, to the global expansion of the universe, so they're moving towards us or moving away from us just because they're in a cluster of galaxies orbiting or very other reasons that we call a peculiar velocity. So if they have a velocity which is in addition to the global expansion, then this will also affect the redshift, so some kind of Doppler effect. So not only are we going to measure redshifting from the fact that they're moving away from us because the universe is expanding, but also if they're moving away from us or towards us, we're also going to see a Doppler effect, which could be a redshift or a blue shift. And that means that the power spectrum we measure in the tangential direction will be different from the one we measure from the radial direction, because the radial direction will be affected by these peculiar velocity effects. So one can measure the two-dimensional power spectrum. In this case, is done in real space. So this is actually the two-dimensional correlation function, sort of Fourier transform analog of this, by looking at transverse direction and radial directions. And instead of, so if we didn't have these peculiar velocities, this would look spherical, so it would be the same in all directions. So intrinsically, the universe has no special direction, so it's the same in all directions. But because of these peculiar velocities, we see these distortions along the radial directions, which are called these redshift space distortions. And in some sense, they're a nuisance because they make it more complicated, but they also have a lot of very interesting information in them. In particular, we can measure the growth rate of the fluctuations using this effect. So you see that by looking at the distribution of galaxies, there's a lot of very interesting phenomena, and we can use different part of this phenomena, different part of the power spectrum to infer different kind of information. And one can do this and combine the results. So this is, for instance, a measurement with the BOSS survey, which a few years ago, which was at the time the largest redshift survey used for this purpose. And you can see this is the correlation function. So this is the Fourier transform of the power spectrum as a function of scale. So again, this is this time real scale in megaparsec. This is the amplitude of the fluctuation. One of them is in the tangential direction, and one of them is in the perpendicular direction. You see that they're different for various reasons, and you can fit this using a model of our standard model and prediction for our standard model, and constrain our cosmological model. In particular, we can constrain, for instance, the amount of dark matter here, or the amount of matter, and the equation of state for dark energy, which is here plotted here on the y-axis. You can combine these measurements from BOSS. In this paper, they combine the measurement from BOSS with cosmic microwave background measurements. With different combinations, you get stronger and stronger constraints. And again, you get something consistent with about 30% for the amount of matter in the universe, and an equation of state consistent with a cosmological constant -1, with an error of 10% or so at the time. Again, you can now assume that the dark energy has an evolving equation of state, and then you can constrain again this equation of state and its evolution, and again you get something consistent with a cosmological constant, which will be here on this point at the intersection between these two lines, with some errors corresponding to about, in this case, quite large errors on W and W0. Okay, so this is what we do if we analyze the position of galaxies, which is basically the distribution of visible matter, or tracer of visible matter through the starlight emitted and other processes emitted by galaxies. Now, what would be nice, as I show you, is if we could get rid of this, right? So if we could get rid of this bias and directly measure the property of the underlying density perturbations, that would be much better, because we could then more directly connect to our theoretical models and avoid all the assumptions or possible issues having to do with this bias model. And that's what gravitational lensing basically affords. And that's what we'll spend a lot of time on in the course, but that I'll introduce shortly here. I think we have 5 more minutes.
Yeah.
So gravitational lensing effect is illustrated in this diagram. So you imagine you have an observer here on Earth, and you imagine that you observe a distant galaxy in the background. Now, if the galaxy if there's no density perturbations along the line of sight between the galaxies and the observer, then the light would travel in a straight line, and we would see the intrinsic shape of the galaxy. Nothing special. But if there's a density perturbation around the line of sight, okay, let's say a cluster of a galaxy, or anything, then the photons, as they travel from the galaxy to us, instead of traveling in a straight line, they will have a trajectory which is perturbed or curved. And this is a direct consequence of Einstein's theory of general relativity, which says that photons are also affected by the curvature of space-time, which are produced by density perturbations. And again, we'll go into a lot more detail about this later. Now, the beauty of this is that when we can use this effect, so instead of seeing, as a consequence, instead of seeing the galaxy, the intrinsic shape and position of the galaxy, we see a distorted version of the galaxy. And the distortion of the image of the galaxy will depend on the density perturbations between the galaxy and us. And the beauty of this is that we can use this distortion, the apparent shape of the galaxies, the observed shape of the galaxies, to infer the mass distribution along the line of sight, of the lens. So this is called lensing, so this is called the lens, this is called the source. And we can infer the mass distribution of the perturbation between us and the galaxies. So as a result, we can be directly sensitive to the mass fluctuations. Yeah.
To infer that the image of the galaxy is distorted, do we have any true image of the galaxy so that we can...
So that's a very good question. We'll discuss that in great detail later on. But of course, we don't have the intrinsic shape of the galaxy. We don't know what it looks like in the absence of lensing. So there are different ways of going around it. We can go into the very strong lensing regime where the distortion is so strong that basically the intrinsic shape of the galaxy doesn't matter very much. It's completely, the observed shape is completely dominated by the bending effect of the light. Or we can go into the weak lensing effect where we can average over a very large number of galaxies which are on average randomly oriented and look for coherent alignment of the galaxies coming from the lensing effect. We'll go into that into great detail. So the advantage of lensing is that we can directly probe the mass. Since the matter in the universe is dominated by dark matter, this means that we can basically directly probe the distribution of dark matter, and we can compare this directly to structure models, our model of the universe and model of structure formation. And this is now done with increasing precision. This is a map, mass map done, one of the latest mass maps done with the sort of one of the state-of-the-art survey called the Dark Energy Survey. This was actually done by my postdoc in ETH, so we're very proud of this. This is done with the initial data of the survey. Again, we'll come back to this in great detail later. But what you see here is basically a map of the projected mass between us and distant galaxies. The red regions are over density, the blue regions are under density, and the greens are intermediate. And you see that there are a lot of fluctuations coming from perturbations, the density perturbations in the universe. By the way, it was not only done by her, but also by Vinu Vikram, which at the time was at UPenn, an Indian postdoc over there. So we're also proud of that too. So we can also take these maps, and now there's no better maps being done now with more data. We're currently working on this, and there are other surveys working on this as well. But we can take these maps and again do an analysis of this fluctuation like we did for galaxies or the CMB. We can look at the power spectrum or the correlation function of these fluctuations and measure them. And you see the measurement here. So you see the fluctuations in the mass as a function of angular scale in this case. So sort of the inverse Fourier transform of the power spectrum of the CMB, but this time for the mass fluctuations. The nice thing is that we can also do it for galaxies at different redshifts. So we can do this in sort of 3-dimension. We can get 3-dimensional information by doing for galaxies at different redshifts. We give us information about the structures at different redshifts, which give us a number of correlation functions. And then we can use them and compare it to our prediction for our cosmological model shown here, and again get constraints on our cosmological model. In this case, this is a constraint on W and in the y-axis, and here is on the amplitude of the fluctuations from inflation as is measured today. And again, by combining all these different measurements with Planck and so on, we could get constraints which are consistent with a cosmological constant again, with an error about 5-10% or so. And here the advantage is that we don't have to make any assumptions about the relationship between visible matter and mass. We're directly measuring the mass fluctuations. And that's the great strength of lensing, and that's why we're focusing on this in this school. Now, the downside of this, of course, there's no such thing as a free lunch, as people say. But the disadvantage is that it's a much harder measurement, of course, because we have to measure very small shape correlations in galaxies. So these measurements are more difficult. It's much easier, and we get much higher signal to noise by measuring the density perturbations in the number of galaxies directly. But with the lensing, we don't have the difficulty of having to invoke a relationship between visible matter and the mass, and dark matter, basically. So, and that's what I'll be also focusing and telling you about some of the difficulties and how we get around it for measuring this weak lensing effect. We can also do it in clusters of galaxies, so clusters of the largest overdensities bound objects in the universe. We can also use these clusters and measure the lensing effect. Here you see these arcs are the very strong distortions in background galaxies, images coming from the cluster of galaxy here, one of the largest cluster called Abel 2218. We can map these clusters, we can measure their mass, and then we can count the number of clusters as a function of mass, as a function of redshift, and study them. We can also study clusters in other wavelengths, either in the optical by looking at galaxy members. The purple here is an X-ray intensity map that shows the X-ray gas, which also gives a measure of mass. So another cosmological probe is by counting and looking at the statistical properties and the distributions of clusters of galaxies through lensing and through various other probes as well. And finally, the last probe, which is a purely geometrical probe, is supernovae, which are used. And so supernovae are basically explosions, very, very energetic explosions of stars at different stages. And it turns out that these these explosions are very regular, so we see them as variable objects with the light curves as typically like this, as a function of time. This is the brightness. After some rescaling, they have very regular properties, and they can be thought as a standard candle. So you can, after some processing, you can think of them all having the same luminosity. So if you can measure the luminosity, you get a measure of distance, at least up to a factor. And then you can plot what is called the Hubble diagram, which is the redshift of the supernova as a function of its effective distance, basically. It's called the Hubble diagram, and you can compare with different models with different amount of dark energy and so on. This is a classic paper by Permuter et al. There's now much better measurements than this. And from this, you can constrain the cosmological model, and in fact infer both the amount of dark energy and the statistical properties and the equation of state of dark energy. So together, by combining all of this information, we basically arrived at what I discussed before, the lambda CDM model, which is basically the standard model of cosmology, which has a cosmological constant, cold dark matter, baryons, which are basically standard model particle physics particles, and as well as photons and relativistic particle radiation, inflation, and general relativity. And all of that combined is extremely well constrained and fits basically most or all the observations, at least on scale larger than galactic scales. On scale smaller than galactic scales, the astrophysics becomes more complicated, and there's some discrepancies, and there's a lot of research trying to find out whether it's because of astrophysical effect or failure of the model. And this is only the beginning, because we have a large number of instruments that are being planned or are ongoing, just started to be operational, to make even more precise measurement of all the statistics I showed you before. There are further experiments of the cosmic microwave background that are ongoing, especially for the polarization. There's a large number of experiments in the visible and the near-infrared, both with imaging and spectroscopies, which will measure both the weak lensing, the density perturbations of galaxies, and many other, and X-rays and so on. Actually, that's not visible in the infrared, but there are also X-ray experiments planned as well. With ever and ever precision. Basically, we're going to get effectively a full sky distribution of galaxies over very wide restive ranges in the next 5 to 10 years. And in this coming year, there'll be a lot of new results coming out for some of these experiments. There's also a very interesting development in the radio, with various experiments being planned, including the GMRT in India and SKA, which India has joined. Which a way of probing the large-scale structure, this time not in the visible light or near-infrared, but in the radio, using in particular the 21 centimeter line, which traces neutral hydrogen. This is a very interesting frontier for this large-scale structure measurement. One can also do lensing in the radio, by the way. I won't have time to talk much about it, but it's also very exciting. So to conclude, we now have a model of cosmological lambda CDM, which is in very good agreement with the observations. through the measurement of various cosmological probes. So it works very well. It observes, it basically agrees with all the observations, or most of the observations. It's very successful. But as you see, it leaves a number of fundamental questions wide open. What's the nature of dark matter? What's the nature of the even more puzzling dark energy? Does gravity, is general relativity valid on very large scales, or does it need to be modified? Is inflation the right theory, and which implementation is important? Does it really explain all the problems it's trying to solve? So even though we've learned a lot, we have basically uncovered a very large number of fundamental questions in physics, which are thought as to be some of the most pressing questions in fundamental physics right now. And weak lensing has a special place in these measurements, as it directly allows us to measure the dark matter distribution, the mass fluctuation, and as we'll see, is very sensitive to dark energy and can give very strong constraint on dark energy. So we'll be focusing on weak lensing in the course. So to conclude, this is the outline of the course that Anjan sent you, and basically we'll be alternating between lectures from Anjan and I. Anjan will be focusing on the cosmological model, the physics of the cosmological model, through its theory and the basic principles, both the expansion of the background and density perturbations. And I will be focusing on weak lensing, giving you the physics of the weak lensing, how we measure it, the current status, the implication on our cosmological model, and so on. So I hope you'll enjoy the course. I'm certainly very happy to be here. And I'll see you throughout this week. So I thank you very much for your attention.